it would be a nightmare for all of us. That's why I just wanted to make it as shorter as possible. So why the cement industry is? The reason is it's quite obvious. When we look at the world population since 1700, after staying stabilized for 200 years, the population growth was very high, especially during the 20th century. And it seems to be that it's going to improve, and it come to the expectation says that it will come to a stabilized position maybe in the 22nd century back again. What happened with this? The production rates of raw materials also increased considerably because of the population growth and the increasing wealth. And consequently, of course, people needed to construct, as the construction industry became very popular. And following that construction industry, the cement industry, with the invention of the modern cement production technology, became very popular as well. If we follow the energy consumption of the world, according to the International Energy Outlook reference, we can see that especially in certain regions, the energy consumption doubled or tripled. So we can say that the total energy consumption is continuously increasing, and basically the major role goes for the communication side. As we all know, 5% of total electrical energy consumption is used in communication worldwide, statistically, and cement industry takes the majority of this consumption. It's roughly speaking 2%. In a typical cement plant, 60 to 70% of electrical energy used in the industry goes for communication. And the ones who is not familiar with the cement industry, let me explain where the comminution action takes place. There are 3 steps that we implement comminution. One is, of course, fuel grinding. The other one is raw meal grinding. And the third one is the final cement grinding. As an addition to all of these, in order to increase these surfaces, we may grind some pozzolan materials, such as blast furnace slag or some natural pozzolans to grind finer values. So the comminution is very important, and cost-wise, it's very critical in the cement industry. And this made in the competition, especially when the cost issues are getting important in the industry, the cement industry changed their mind from the conventional technology to innovative technologies. In parallel to all of these, especially in the recent years, we are all aware of this Kyoto Protocol, which on climate change, and the countries who signed up accepted to come back down to the levels of 1990, 87% carbon dioxide emissions of 20 or 30 years ago. So when we look at the cement industry, it's a heavy producer of carbon dioxide, and roughly speaking, 5 to 6% of global man-made carbon dioxide emissions comes from the cement industry, and it's basically depending on the chemical reaction there. So in order to produce 1 ton of cement, they produce 0.7 tons of carbon dioxide in their factories. Therefore, carbon dioxide trading is very important for them, because nowadays, roughly speaking, a cement plant's profit is in the range of $10 to $12. So plants have started to budget the carbon dioxide emissions because there is a trade and there's a volatile market. And if we go to that volatile market, if you want to buy carbon dioxide, by today, it reached up to 42 euros. So it's well over your profit. And that's why they have to be very cautious in terms of the energy consumption. And this is where they start to think about innovative. This is a typical conventional dry grinding circuit of a cement production. It's a 2-compartment ball mill running with a classifier. You come down to a certain grind size. Nowadays, it's very fine. A typical number for a cement produced nowadays is D50 values around 12 microns. It's very fine production with a very old technology. And a typical energy consumption would be in between 30 to 40 kilowatts hour per ton for that fineness. After thinking about innovatively, of course, we all know that the compressed bed breakage has got more efficiency compared to the impact breakage, and it's proven. If we check the diagram here, at a certain specific combination energy, we can produce more fines under the compressed bed breakage conditions. And this has been patented and worked with the German scientists, and then a commercialized unit has started in the cement industry. And we all know this as high pressure grinding rolls, or the names known by the cement industry is the roller press. The first roller press was built in Turkey in 1985, and still it's in operation. You see the flow sheet here. This is the recent flow sheet, one of the recent flow sheets. And HPGR is running closed circuit with a certain classifier with the support of ball mill. I will explain the circuit types. You can see two application of air classification to HPGRs, which reduces the typical energy consumption down to 20 to 22 kilowatts hour per ton, from 30, 40 to nearly half of it. Of course, it was not enough. And then a combined version of the high compression system, which is the vertical roller mills. The high compression system is underneath, and on top of it, it's an embedded air classifier working as a unit producing its final cement right now, but it started with the limestone, and for many years, it has been used for limestone and for coal industry. And recently, it's been in operation for cement grinding as well, and with, again, reduced the energy consumption to the same level of, roughly speaking, the HPGRs. Where did we stay in this action as Hacettepe Communication Group? When we started the group, of course, we have two hats on our heads, because we are coming from the mining department, and we have the advantage of closely working with the cement industry, because the number of the cement plants in the country is around 80 right now. So in every 50 kilometer, we have a laboratory plant that we can easily reach and do whatever we needed to do. So we started a program in 1997 called Modeling and Simulation of Dry Grinding and Classification Circuits, with our mining engineering understanding, because the cement industry understanding of combination is totally different. They were thinking about a black box in the meantime. For that reason, we needed to understand the performance of the equipment used in dry grinding. So we started working on the ball mills, the roller presses, HPGRs, vertical roller mills, hollow mills, and the air classifiers. These are the innovative technologies or high compression technologies being implemented in the cement industry. And since 1985, this is heavily used in this industry to reduce the energy consumption and to take the advantages of the high compression system. And we started working on this. And in the meantime, we started evaluating the situation of mining industry. Mining industry has got some challenges ahead, because as we all know, the grades are decreasing and the rock hardnesses are increasing. Again, the carbon footprint is an issue for mining industry, and the grind size is decreased, of course, because of the liberation. Energy shortage is approaching, and the water issue. We celebrated the Water Day I think 2 days ago, it's becoming more and more significant because mineral processing requires larger volumes of fresh water, and also the mineral tailings is becoming a problem, and dry stacking is taking its place. For instance, in Australia, mining industry accounts for 2% of nation's total water use. So it is significant. Typically, industry needs 500 liters for every ton of ground ore. This means that we have to start thinking about dry comminution and then dry processing step by step, because it's after the carbon footprint, the water use will be very expensive for the mining industry as well. If we look the problem from the energy distribution side, we all know that comminution represents at a minimum of 10% of the site production cost, because it's 54% goes for crushing and grinding. And roughly speaking, it consumes up to 3% of all electrical power generated in the world. So the question is, can this innovative technology be moved into the mining industry? Yes, it already started, of course. We all know that with the high pressure grinding technology or with the roller presses, the mining industry started their application. If we look at the high pressure grinding rolls, which was introduced in 1985 the first time, of course, it was started with the cement industry, and it was built for especially treating for more abrasive materials. When we look at the schematic view of the equipment, the HPGR consists of two counter-rotating rolls mounted in heavy-duty bearings here, and pressure is applied to one of the rolls while the other roll is fixed in a certain frame. The rolls are driven by separate motors, and the rolls can be operated either at a fixed speed or variable speed depending on the process. Comminution in an HPGR takes place primarily through interparticle breakage, like you see here. And once the material is fed into the system, there is an acceleration point where the material is nipped, and it passes through the compression region, and the direct contact of the rolls onto the surfaces, and the energy is transmitted through the bed of particles in intimate contact with the surrounding particles. The breakage generally occurs, or preferentially occurs, along the grain boundaries, which we call in time to time as microcracking. And the HPGR product is in the form of a cake if it is operating in under high compression regime, because in most of the mining applications, unfortunately, we couldn't be able to observe this cake formation because of the less power use or less specific grinding force. What about the benefits apart from the energy utilization of high pressure grinding rolls in the system? The high pressure grinding rolls or vertical roller mills or compressed bed breakage systems, first of all, produces more fine material compared to a typical crash size. And all these data have been measured by ourselves. And for instance, in a gold industry, we made that comparison that there's a significant increase in the HPGR product we observed in the gold industry. Roughly speaking, if you are effectively using your HPGR in a hard rock application, we can expect 40 to 45% of -1 millimeter material in the HPGR product. This is typical. Also, we observed or we measured microfractures in the HPGR products under the microscope, but also in some cases, especially within the cement industry, we measured this through the work index change of the bone mill feed. It dramatically reduces the bone work index because of the fractures created in the ore body. If of course the high compression can be implemented on to the material. The other part is, again, in some cases, depending on the mineralogical conditions of the ore bodies, we can see increased metal recovery. For instance, in one cases, we measured two lines. One is running with HPGR and the other one is running with the conventional crushing system, which is feeding the heap leaching operation. And we observed 6% more recovery with the compressed bed system application. But you need to manage the fines produced through that system. This is an extra cost, but it has to be managed. Once it's managed, the metal recovery stays there. In addition to all those, high compression may help selective liberation, especially at coarse sizes. One of our PhD students worked on that. Rather than going down to a grind size, staying at a coarse end, we can achieve higher liberation degrees at the coarse size, which promotes especially pre-concentration in some ore applications. What about the status of the mining industry utilizing HPGRs? I will share 3 different circuit types. All addresses us the coarse grinding or fine crushing section. For instance, here, after a secondary screening operation, 45 millimeter screens is producing feed material to an HPGR, and the HPGR is running in closed circuit with the screen for 9 millimeter screens. Please be aware of the reduction ratio here, because I will show you some flow sheet again from the cement industry and what we can expect from the HPGR. Is this the right place that we use it, or can we improve it in the mining industry as well? So generally speaking, in most of the circuits, we are using the HPGRs as a tertiary crusher stage or very expensive cone crushing application and feeding the ball material. If you implement high compression zone, you may reduce the bond work index, which might be utilized as the energy efficiency in the downstream ball milling operation, or the fines generated can be evaluated as the production increase. This is the only simple advantage that we could be able to get in the mining industry. And the third circuit is, it's more on pebble crushing. After the SAG milling operation, if we have the pebbles coming out of the system, and we can utilize, or we are utilizing the HPGRs to crush these pebbles. So what can we expect from an HPGR if we look at the story from the cement industry back again? So you will see 5 different type of application or circuit type in the cement industry. Chronologically, in 1985, when it started, the HPGRs automatically started running an open circuit mode. So it was used for specifically feed preparation to ball milling operation. And afterwards, the operators noticed that because of the requirement of adjusting the feed going into the roller press, they splitted some of their products back onto the HPGR in order to increase the confined bed conditions. So they needed some fine materials. So this brought the idea of the hybrid operation, because the HPGR is running with a ball mill, and ball mill is running with a dry classifier. Some portion of the very fine material can be sent back to the HPGR to increase the compressed bed conditions. Afterwards, the industry realized that the HPGRs produces significantly fine material, And if an appropriate classifier can be used, then the production rate or the advantage can be maximized. And this is the closed circuit application of the HPGR, and running again with a ball mill circuit. Afterwards, again from the HPGR circuit, the fines generated can be used as a direct product. That's why 2 stages of classification is implemented, and this circuit type is known as semi-finish grinding. Right now, we come to a certain point that the HPGRs can be used with a certain classifier to produce final cement, very fine material. D98 is below 40 microns. If the air classifier is suitably designed for this process, it is running very effectively, and we have plenty of data in hand in terms of this finish grinding. Why the circuit types are important? Let me explain you with some data that we collected from a closed circuit application. Here, you see the feed going into the system is 18.5 millimeter F80 size, comes down to 60 microns just in an HPGR circuit. We are talking about a reduction ratio of, roughly speaking, 300 at 8 kilowatts hour per ton, including the fans, including the classifier, and including the main motor. So the significant work being done with high pressure grinding roll system. And this is typically fine. Of course, it's not, in this case, it was not sufficient for the final cement to produce the required strength. Again, at the ball milling with the air classifier is used to grind from 60 micron down to 28 micron. So in order to achieve this reduction, we are spending 13.6 kilowatts hour per ton. So in total, it is 22 kilowatts hour per ton from a starting point of roughly 20 millimeter down to 28 microns. But the majority of the work being done with the high compressed systems here. You can see the fully size distribution around the system. This is the typical HPGR product from a closed circuit. You may notice that we are receiving a steeper size distribution. The reason is that as we get the immediate action of fines generation pulled out by the air classifier from the system, and this gives the energy advantage of the equipment. What about the air classification? This is a typical performance curve of an air classifier, and you can see that it's in the range of 20 to 25% bypass value, which looks like an hydrocyclone operation. Can it be more effective? Yes, it can be. But in terms of the energy consumption wise, if we think the open circuit HPGR spending 100% specific energy consumption, this can be reduced to roughly 50-55% by changing just the circuit type. So the HPGR's route is from open circuit to closed circuit. How will we achieve this? To achieve this, we need the classification, dry classification, or in other words, air separators. The first air classifier was patented in 1885 in response to the need to grind large volumes of the material. And in the technological development, it developed 3 types of air separators. One is the static version, the other one is the dynamic version, and the recent one is the combination of the static and the dynamic version. The forces acting on air classification can be split in 4. Of course, as we expect, the gravitational force is very dominant. A drag force implemented by air velocity, centrifugal force created by the dynamic part or by the rotor cage, and the impact force which prevents the material to stay in the classification zone. This is a typical static type separator which was developed to be used in combination with high pressure grinding rolls. As I said, a cake is formed by the high pressure grinding rolls, and that cake should be deagglomerated before separation, and the agglomeration is occurring in here. So this V separator is designed both for deagglomeration and for classification, and the fines material can be sucked out by a fan filter which exists at that point, and the coarser part which settles down can be circulated back onto the equipment. So the feed is directed down through baffles to meet the rising airflow. The V compacts are broken as they collide with the baffles here. In a typical cement application, we can expect to receive a P80 value of 200 microns from the fine section of a V classifier, which is running with an HPGR. If we have a look at the data coming from the industry, this is the performance curve of the V separator. Because of the high circulating load, the efficiency seems to be lowered. The bypass value is 50%. This means that the circulating load ratio is quite high, which provides us a very steep size distribution at that point. The other version is the dynamic classifiers or dynamic separators, where the material is first dispersed on the distribution table and falls down into the gap between the cage and the guide vanes, forming a thin curtain of material here. After passing through the vanes, the air moves into a horizontal vertex, and the air carries the fine material tangentially across the face of the rotor, which is turning in the same direction as the vertex. So the separation can be controlled by varying the volume of the air flowing through the separator, which is, as you increase the volume, the product becomes coarser. By changing the speed of the cage or by increasing the centrifugal force, the fineness can be increased. Also, the other static controlling point is the guide vanes, which comes from the design. But during the control room, with a simple adjustment of the airflow and the rotation of the cage, you can easily adjust the production or the size. Chronologically, the development of the dynamic separators started from the first generation to second, and recently the high efficiency separators are in operation in many applications. As you can see here, that the air use in the classifier is quite critical, and with the high efficiency separation system, we can reduce the bypass as below 10%, and we can achieve very steep or very efficient separation if the classifier is suitably designed according to your material. The other version, which is quite interesting and has already started to take role in the mining industry as well, especially in the iron industry, it's a three-product dry classification system. So V classifier is combined with a dynamic classifier. The feed comes from this direction, from the HPGR. The coarsest particles can be directed back to the HPGR or can be utilized for pre-concentration at that point. The fines goes directly into the dynamic mode. There is a rotor cage here, and of course, the air velocity or air sucks the fines out from the system as a fine product, and the coarse product from the dynamic section can be evaluated in another system or can be sent to again another concentration level. The importance of using this V type of classifiers is you can implement hot gas or fresh air to dry your material as well. This is a very typical application, especially in high moisture content of cement material, especially in limestone and clay. The hot gas can be used to dry the material. This can be a solution for the high moisture content hard rock applications. If we look at the VSK separator performance, as you see that in the dynamic portion, we have a very high efficiency of classification action occurring, and a sharp separation can be achieved through this system. What about the vertical roller mills? We talked about the high pressure grinding rolls, and I mentioned about the high pressure grinding rolls, which can be utilized to produce final cement with a suitable classifier. Vertical roller mills is the ancient technology of this technique. On the left-hand side, you can see a 1 horsepower mill, which was used for grinding food. And this is the recent version, maybe over 1,000 horsepower mill used for grinding either minerals, cement, coal, or limestone. So the human being knows this technology since from the mid-age, because of from the muscle power down to a very strong motor power, which we implanted in the vertical roller milling technology. So if you look at the vertical roller mill working principle, we have a grinding table here, and we have the rolls, which is implementing pressure, and with the rotational speed of the grinding table, the feed material coming onto that table is directed underneath of the high compression zone, and the air flow, which pneumatically carries the material to the air classifier, staying on top of the system, which is used for fine classification. The fine material is coming out from the system as a final product, and the coarse material is directly sent back to the grinding zone here. It's a unique material. It's 1 unit. Everything is included. It's the grinding action, and the classification is in 1 unit. It is running as a black box. You can only see a fresh feed coming into the system. You can follow the fine product coming out from the system. The internal action was a question mark. You see the feeding system, the rotary valve, which you direct. This is the comminution zone where the compaction and grinding is occurring. Mill table and the gearbox and the electric motor is the main part of the equipment. Of course, the classifier that the gas inlets are used for the separation in the system. You can see the schematic view of the operation. The feed comes into the system, and the product fine material is coming out from the system. All the grinding action takes place at that point. What about the benefits of vertical roller mills, energy-wise or maybe metallurgical-wise? There have been lots of work being done on this, especially on cement side. 30% energy saving can be provided by direct OVRM grinding. This is proven. That's why the industry or the new or the greenfield projects immediately goes for vertical roller mill application even in cement grinding as well. What about the metal production? It's been tested for zinc, and it's been observed that as a comparison to egg SAG ball mill, it consumes 40% less energy use with vertical roller mill. It was completed one Wayne Pandrunik. We had a chance to work with the OGP plant of Lösche company for more than 6 months in Turkey. We had the chance to evaluate different ore bodies, different mineralogies, and we observed that at least 18% less grinding energy consumption can be achieved compared to a conventional wet ball milling circuit. Copper slag application is very predominant, and there are lots of copper slag operation, especially in Asia, in grinding. And in this case, the overflow mode of the vertical roller mills have been implemented. But by saying the overflow mode, the typical vertical roller mill design is air swept. You transfer the material pneumatically. But it's well known that if we have chance to transport the material mechanically, which is an overflow mode, we can have more energy advantages in the system. Also, some researchers indicated the positive effects on performance of downstream processes like flotation and leaching. In one study, it's been proven that flotation recovery of copper and nickel was increased from 74 to 84%. And also, again, in zinc recoveries could be obtained at higher levels or higher recoveries at efficient energy use. Again, this study comes from our gold application. We measure the higher gold leaching performance if we implemented a VRM system. The reason that is the microcrack propagation is immediately utilized by the downstream process. In this system, we do not have any other comminution process which kills the microcracks being created by the high compression system. So everything in one unit. We observed low wear rates. Also, in terms of the floor space, it's less floor space are required. Therefore, vertical roller mills seems to be advantageous for the mining industry in the future as well.
Hello, how are you?
In order to understand the vertical roller mill performance,
I'm already at work, so I'm fine. Yeah, how are you?
In order to understand the performance of the vertical roller mills, we needed to separate the comminution and the classification action. Therefore, as a group, we created a new technique which includes the crash stop of the vertical roller mills during the operation. This is the schematic view of the operation here. We have the grinding table. We have a static classifier. It's not actually a physical classifier because pneumatically the material is transported to a certain level, and because of the heavy load, some portion of the material is bypassing back onto the grinding table. And we call this as a static classification effect because of the air. And the residue goes pneumatically onto the dynamic classifier where the classification occurs. We receive a reject from the dynamic mode and we receive the fine products coming out from the system. Usually, we have the chance to measure the fresh feed and the final product. And in some applications, there's a grid cone here where coarsest material can be transported mechanically back into the system. So we can only measure all these. So we do not have any understanding what's being happening internally. That's why, as I said, we started to crash stop the mills, and we are getting samples around the grinding table from different regions to address first the grinding action and to understand the mass balance within the system. Therefore, we have been using an iterative mass balancing technique to find out the best flow rates. And this has been tested with CFD studies, and this is the state of art of the group in order to sample the vertical roller mills. I'm going to show you one sampling action here. You can see that it's grinding limestone and cement raw material with a motor power of 700 kilowatts. These are the operational data. It's roughly speaking 98 tons per hour material is coming into the system. And we stopped the mill, we got the samples, we mass balanced the circuit. You can see that this is the product coming out from the system, and the fresh feed coming into the system is here. So you can see that there is a very high circulation within the system because everything is occurring, and the grinding under the rolls are very small. Especially the reduction ratio of the grinding is not big. So this is the value of this equipment. Very high circulating load ratio can be achieved. These are the tonnage values of that mill. At 98 tons per hour of fresh feed, our table feed increases up to nearly 1,400. So we are talking about a circulating ratio of well over 1,000. This is the majority of the pneumatic transport is bypassing because of the static separator. So 600 tons per hour directly goes back to the grinding chamber, and the residue goes up to the classifier to receive 100 tons per hour product from the system. So as you see that, there are two classifications happening, and as expected, very inefficient static separation because of the pneumatic transportation system, and generally speaking, a high efficient classifier is being used in the vertical roller mills to achieve the final product. But the major problem is inevitably we have no chance to carry whole material up to the classifier, and this makes a very high circulating load within the system. You may think that this is very inefficient, but in terms of the design conditions, this has been taken into account, and therefore the producers select a bigger motor size in order to achieve a certain grind size. Because of that high circulating load ratio, because as soon as you reach the fine material, it's been extracted by the air classifier from the system, the product coming out from the vertical roller mill is very steep. Is this a good thing? It's good for minerals industry because you produce less slime, but it's not good for the cement industry. The cement industry is addressing the side effects because of the steep side distribution, especially because of this surface area, the strength value is dropped. And compared to a typical ball mill application, in order to achieve the same strength value with the vertical roller mill, the cement producers has to grind finer. So some of the energy advantage is consumed because of the quality loss of this steep side distribution. But this can be an advantage for the mining industry. Of course, working deeply with these equipment and also working working with the pilot equipment, we had the chance of evaluating the operational parameters on the performance. So the dam ring height is quite important, where you adjust your grinding condition in a vertical roller mill. As you increase your dam ring height at a certain point, the grinding bed height is increasing, and then it's stabilized. And if you increase the dam ring height, your product size gets finer, and the steepness of your material is dropping. Again, the other effective parameter is the pressure. So once you increase the pressure, the production rate increases because you are producing more fines. Inevitably, especially as soon as you produce fines, the air suction takes the fines out from the system. But if you increase the pressure, of course, the production rate increases pretty much in the normal range, specific energy. consumption stays constant, while of course, the mechanical power is increasing. With the pressure value, of course, the product gets finer and the grinding bed height reduces. These are all important for us to evaluate in our modeling studies. At the same time, we focused on the airflow, and if you increase the volumetric airflow to the system, the mass flow from the system is increasing. You are getting more product, and the circulating load is reducing with from the system. Of course, the increased volumetric airflow ends up with the coarser product size, and the steepness is affected as well with the volumetric airflow because of the reduced bypass of the dynamic classifier. Of course, we are using a classifier rotor speed, and if you increase the classifier rotor speed, because of the centrifugal force increase, we are getting finer product from the system. And the last effect in the vertical roller milling is the grinding table speed, which affects the residence times of the material in the grinding chamber. And this must be optimized during the operation because of the vibration limit. And this vibration basically depends on material properties such as particle size distribution or grindability of the material. Having all these information, including the high pressure grinding rolls, vertical roller mills, and air classifiers, it brought us to work on the modeling studies of these equipments. Until now, since for 25 years time, we collected all these data. You can see the data being collected from industrial applications, all well-defined, comprehensive, and material characterized materials have been used in modeling purposes. In here, I will concentrate on high pressure grinding run, vertical roller mills, and air classifiers. The rest are under operation, or we have the models for them as well because we have significant database in hand. But in addition to our industrial data set, especially for mining applications, we needed to use OGP mobile plant and in-house pilot plant, which we built in our laboratory in Ankara. For the breakage modeling of compressed bed systems, we choose population balance model. I won't go into the details of the models, but we have to know the breakage rate and we have to know the breakage characteristics of the material, provided that we know the mill content. So for the mill content, if it's the HPGR, the material in between the rolls is the mill content, and the material under the rolls in the vertical roller mill is our mill content. Geometrically, by utilizing the dimension of the equipment, we can calculate the mill content. So how we used all these data sets, we knew the feed and product, and we characterized our material by using piston and die test. And then we managed to back calculate the breakage rates for different design and operational values or different material characteristics. Generally speaking, we have the same approach. Rate varies with particle size with a constant of A and alpha. A is the function or A depends on specific grinding force, which represents us the geometrical condition and also the operational pressure value. And also we have a material softness or material index, which I'm going to define later. And also we needed to define the feed size distribution going into the system, which is defined by alpha. And we address this with the specific surface area. But if you look at the line here, the lower end, because of the less specific grinding force, comes for the hard rock application. And for the cement clinker, we have higher specific grinding forces. But at the end of the day, everything lined up on the same line. So we could be able to model the HPGR by using this. The same approach has been taken for vertical roller mills as well. So you can see the specific grinding force, material index variation for A. This is typically for minerals industry utilizing pilot scale data. It's chalcopyrite and polymetallic ore. It all lines up in the same place. And again, the alpha is varying with the specific surface area where we define a particle size distribution. After making or after developing this, we can be able to make any prediction according to any design value of or operational value of a vertical roller mill or HPGR by utilizing this modeling technique. We do not need to do any model fitting anymore. So we can use the models for either brownfield operations or greenfield operations. I just want to briefly mention about the material characterization technique for piston and die testing, which is the group protocol. What we do, we use a typical piston and die, and we have a typical test matrix of different 3 different size ranges and different energy levels, and we obtain typical data after piston and die with size effect. You can see that the size effect here. So we reflect this effect on T family T10 curve by implementing the size effect with varying energy levels. We can define by using this T family curve the breakage rate function, breakage distribution function. But the other parameter which I addressed as material softness or material index, where does it come from? Again, it comes from our characterization technique. This is the material, we call it material resistance to compression, or in other words, during the operation, we measure the disappearing rate of the top size particle under piston and die. So at varying energy levels, we measure the disappearing rate. Then according to the equation, we calculate B multiplied by C, which is the material softness. And this goes well with our model structure. So once we have the material, if we run a piston and die test, we can both calculate breakage distribution function and material softness, which goes into our model structure as an input. You can see the material resistance for different ore types we measured. Finally, of course, we are talking about the closed circuit application. We are talking about the air classifiers. Our tendency to work on the air classifiers with the existing database was on the efficiency curve approach, which is Whiten's approach. So that's why we needed to find out the bypass, fish hook, D50 cut size, and the sharpness. So you can see the database of varying efficiency curves with the corrected and reduced efficiency curves. Our inputs into our model structure is the rotor diameter, separator diameter, the fan capacity, feed tonnage, feed size distribution, and feed fineness. As an output from our modeling structure, we can find out the fine and reject size distribution, fine and reject tonnage, and of course the Tromp curve of the separator. How do we achieve this? We achieve that the dust loading of separator feed is varying with bypass in a linear form. Again, the cut size is affected by airflow and the rotor speed, also the amount of fines existing in the feed coming into the air classifier. So our air classifier model runs in a dynamic mode. As your feed going into the classifier changes, the classification performance changes. Of course, the dust loading of separator feed is affecting the sharpness, and the diameter of the separator is again effective on sharpness. So the ratio of separator diameter to dust load gives a linear relationship for the sharpness of the separation. We set up a link between bypass and fish hook, which is linear, and by getting out all these values, we can easily predict the performance of the separator, and we can combine this model with our compressed bed breakage model system, and we can run any closed circuit with HPGRs or with vertical roller mills. If I conclude, what I'm trying to explain until now is the technological changes are occurring from cement to metal, step by step. And the high pressure grinding rolls was the first step, and it's in open circuit application. Recently, by some, especially in iron industry, there are some closed circuit applications have already been started, and this is encouraging, but there are challenges. The major challenge is the moisture. How do we handle the moisture? Will we dry it, or will we increase the operability of the material under the moist conditions? I'm addressing some surfactants. Can we use some surfactants in order to be able to handle the wet material in these systems? The other one is the mechanical implementation of higher specific grinding forces, especially in hard rock applications. At the moment, a specific grinding force, we have a certain limit. I'm pretty sure that this mechanical implementation will be achieved with some improvement. Also, some dry pre-concentration technologies are required for selective breakage operation in order to get the advantage of selective breakage of these systems. In terms of the modeling approach, is we approach the problem with a practical view or with a semi-empirical approach. So the fundamental modeling of compressed bed systems is required, and many researchers, even in GCC, have been working on this. And especially the vibration problem has to be addressed, which is the function of the material properties. Again, the hardness and the particle size distribution and the mechanical conditions of the system. Maybe by utilizing computational fluid dynamic systems, better air classification efficiencies can be obtained, especially for the static operations, because at the moment, the efficiency of the V separators, even the V separator, is too low, and this requires a very big or giant machines in terms of the handle mass production. Segregation, especially at the feed end of these systems, is a problem. So optimizing the segregation or optimized feed preparation is very important. And this can be achieved by fundamental modeling approach. And also, especially in high pressure grinding roll systems, the pressure gap relationship, we know how it's differing, but we cannot understand how the material properties are affecting this pressure gap relationship, because the material properties and the dimension of the HPGR is very dominant in this change. We can follow these from the trend analysis. Until now, we couldn't be able to address how the material properties are affecting this change, and this can be addressed by these fundamental modeling studies. What about our group? When we started understanding the performance of the equipment, at the moment, we completed the modeling studies for ball mills, roller presses, air classifiers, vertical roller mills. I won't touch dry storage milling. This is a separate issue, but we have the model structure with multi-component behavior and with some surfactants. We have a dry grinding simulator in-house, which we can utilize for evaluating different flow sheets for cement and for minerals industry. Also, we have a breakage characterization protocol for high pressure systems to understand how the breakage occurs in the system. I would like to thank you for your patience. And if you have any questions, it's a pleasure for me to answer if I can.
Okay, thanks a lot, Hakan, for the fantastic presentation, overviewing a lot of work you guys have been doing over decades now, isn't it? And excellent, thanks.
23 years.
Indeed, 23 years, excellent, very close to a quarter of a century. We ran quite a bit over time here, but perhaps a few of you want to put some questions for Hakan. I'm sure you will have.
If I might come in here first, thank you very much, Hakan, for this interesting presentation. For me, question is still open. If I have a gold ore in my mine, what should I use, an HPGR or a vertical roller mill? What would you suggest and why?
It depends. I can immediately answer that question because I have the advantage to make a comparison of leaching and flotation. If you are implementing bleaching, high pressure grinding rolls. It's the direct way you should go. But for the flotation, vertical roller mills is superior in terms of the higher recoveries. This is the measured data. That's why I can speak confidently.
Okay, thank you.
Hello.
Okay.
Yeah. I have also a question regarding you. Thank you very much for the paper, Hakan. I'm just looking also on trying to understand the position of the equipment in the flow sheet. You really express nicely about the HPGR. And do you believe that the VRM it's taking the same position in the flow sheet for mining industry, or completely different?
No, absolutely. For vertical roller mills, I'm very positive in that manner. Again, I couldn't be able to have a chance to present what's being done on the pilot mode, but energy-wise, in one case, in a gold operation, I can immediately share some data. The recovery improvement was measured as 5% in flotation, and the energy advantage compared to conventional ball milling circuit was around 14%. And on top of this, the steel consumption was reduced. And this was a surprise to us as well, especially the major operational cost income came through the steel consumption. And surprisingly, the payback period was very shortened because of just the less steel consumption. So yes, I see the vertical roller mills have a big advantage in moving into the mining industry.
Okay. And regarding the wear issue, if I can just ask you, is it a problem for the time being from cement going to mining industry regarding the wear rate and solution that normally companies provide, suppliers provide? Or with the current situation, what is the situation now? Is it okay, or do you see any improvement needs to be done again?
With the hardened material, it's already been solved because, as you know well, the blast furnace slag is a very abrasive material, and it's very well processed in the cement industry with a very less steel consumption. The wear rate is not a significant issue for this at the moment, especially with this hardened material.
Even for HPGR or vertical roller mill, that's the same
Absolutely.
Okay.
I don't expect a significant problem in that manner.
Okay.
Provided that those equipments operated in a positive manner by saying that if you feed, say, with a segregated feed, if you let vibration occur, then different breakage may occur on the surfaces. But in a normal wear rate position, I can say that the compressed bed system has got some advantages compared to conventional systems.
Okay, thank you.
Okay, thanks. I guess Aubrey or Sherry wants to make a comment there, correct?
Thank you, Hakan, for a very good presentation and very insightful indeed. Just going back to maybe the question that Hoga asked earlier, don't you think the driver in terms of where you apply the vertical roller mill and the HPGR is dependent on the classifier? For instance, if you use the screen in conjunction with the vertical roller mill, you have a very similar effect to the HPGR and the screen, and therefore it can be applied for leaching. But when you use the dry air classifier, as the case is in most of the systems, then it's much more amenable to flotation.
If I get it, you're right. Yes, you mean the in terms of the moisture. You're saying that the vertical roller mills can be implemented in terms of the hot gas generator application, isn't it? The question you asked?
Yeah, if you use the VRM with a screen instead of a VRM with an air classifier, it can also be very good for leaching because it's still compression grinding, and you just shift the cut.
Thank you for. I already forgot this, and thank you for supporting. Yes, it's of course, it's an overflow mode operation of vertical roller mill, and some tests have been conducted on this as well. Yes, I totally agree with you.
I have a question. Thank you very much, Hakan. Very interesting presentation. I had a few sort of general questions, but I think I will ask more of a detailed technical question from the VRM, vertical roller mill. So you showed a few slides on the effect of the table speed and the dam ring and then the pressure. And I was just thinking, have you sort of analyzed the trade-off, like if you would go with a lower table speed and a high pressure versus, let's say, a higher table speed and a lower pressure, sort of at a sort of equal specific energy? Would there be a difference, or what do you think?
Yes, it's a very good question. There is an optimized point which you adjust with the dam ring height, and you can adjust the dam ring height according to your material properties, especially the p-size distribution going into the system is very critical. So at different levels, you can achieve this, and the best is the palleting in that manner.
So if you increase the dam ring height, I would presume that the volume of material comminuted or sort of, you get a higher volume of material in the comminution zone. Is that right?
Yeah, it is, but up to a certain level, because afterwards you can end up with a cushioning effect. So there's a certain point, there's an optimized point.
Okay, thank you. Interesting.
I have also another question, because I have all the guys, all the experts around the table. When I listen to you, Hakan, and you see the characterization that you provide for the rocks and minerals, I think, is it no synergy with what Magnus is doing with the cone crusher regarding the same kind of equipment, tool, dion and the piston and dion system? And we are both in compression as well. So I don't know if together you had some cooperation and looking on the same kind of equipment or same kind of test. Is there any synergy between the both equipment?
Absolutely, you are right. That's why we are under the umbrella of GCC logo. So we have been working on this. So yeah, there's a joint protocol. And
because for a supplier, it makes sense that in terms of characterization, you do not have too much type of test. You know what I mean?
For us as well.
Okay, I'm on the same page then.
Hakan, a question for you with regards to between the HPGR and the vertical mill. Any difference on the size of the input of the ore in mining? Is there a difference that one can take larger material than others, or are they basically equal in that side?
Yeah, it's a very good question. In HPGRs, if you go to a larger feed size, obviously you have to increase the diameter of your rolls, and if you increase the diameter of your rolls, your operational gap will be increased. That means that you will receive a coarser product size. Therefore, in a typical application for HPGR, I can suggest feeding sub 40 millimeters, which will be effective, and the dimensions of the equipment can be designed accordingly. For the vertical roller mills, if the material is softer, such as limestone, you can go up to 75 millimeter, but in a normal application, I can say that it's around 50 millimeter.
Thank you very much.
Pleasure.
Excellent. Other questions, fellas? We ran a little bit overboard here, but the topic is definitely quite enticing. So it will be enough for a couple more presentations. So last chance, please.
Yeah, perhaps I can come up with another question. I mean, In a HPGR, you have typically the pure compression forces, more or less. While in the roller mill, depending on the shape of the rollers, you have quite different. You don't have just compression forces. If you have certain rollers, you might have quite a bit of shear forces. How does this influence the process?
Yeah, you're deadly right. It's influencing our breakage rate. The shape of our breakage rate is totally different. If I make a comparison of the HPGR breakage rate with the vertical roller mill breakage rate, we can observe the effect of shear rate or shear forces. I cannot quantify how much. That's why I mean a fundamental study could be implemented in that stage.
Thank you.
Well, so a last chance for a question there for Hakan. So if not, let's give a nice round of applause, I suppose, to him. And definitely, we'll be looking forward to have you here next month for yet another interesting seminar on a particular topic in comminution. So thanks a lot for everyone for joining in these difficult times, but it's a nice moment to be together every month here in this great forum. Thanks again, Hakan, for the great presentation, and looking forward to see you again next month.
Thanks a lot.
Okay,
thanks everyone. Cheers.
Thank you.
Great to have you here.
Indeed.
Thank you.
Bye.